Alright, so today we're going to have a look at topic 8, quadrilaterals, and we'll break topic 8 into two parts. Today we're going to have a look at part A, which includes the main properties of quadrilateral basics, trapezoids, parallelograms, and rhombi. And in our next lesson, we're going to have a look at rectangles, squares, and statement if and only if. So what does this mean? And quadrilateral problems. Okay, first, basics of quadrilateral. So what is a quadrilateral? As shown here in figure 8.1, a quadrilateral ABCD usually has 4 sides, 4 vertices, and 4 angles. Actually, there are 2 types of quadrilaterals, and in this course we'll mostly focus on convex quadrilaterals, which is shown on the left side, figure 1.8, in which all interior angles of the quadrilateral are less than 180 degrees. Of course, there is another type of quadrilateral, which is a concave quadrilateral, which is shown here in figure 8.2. But in our course, we'll only focus on talking about the convex quadrilaterals, which is shown on the left. Can you follow me? Okay, and one important property of the quadrilateral is that the interior angles of any quadrilateral add to 360 degrees, including the convex or concave quadrilaterals. Can you prove this? Okay, I'll give you 3 minutes to have a look at these problems, and then we'll have a look at the solution together. Try to prove this is actually true for any quadrilateral. Alright, have you finished? Okay, Neil, can you explain your proof to the other students?
Okay. So we draw a line from like two of the opposite points, and then it splits like the quadrilateral into two triangles. And the sum of the interior angle of the triangle is equal to 180. So the sum of the angles in the quadrilateral is equal to 2 times 180, which is 360.
Yeah, thank you very much. Okay, so usually when you want to prove something, you can start from what we have already known, right? So in this case, we can connect point A and C, just like Neil told us. And we already know that the sum of the interior angles of a triangle is 180 degrees, right? So let's call this angle 1, angle 2. This angle is 3, and this angle is 4 here. So we know that angle 1 plus angle 2 plus angle D equals 180 degrees. And on the other hand, if you think about triangle ABC, then we know angle 3 plus angle 4 plus angle B is also 180 degrees, right? Therefore, we know angle 1 plus angle 2 plus angle D plus angle 3 plus angle 4 plus angle B equals 360 degrees, which means angle D plus angle DCB plus angle B plus angle BAD equals 360 degrees, which means interior angles of this quadrilateral add to 360 degrees, right? So for the other quadrilateral, you can use the same method to prove this statement is actually true, right? We can connect E and G. Then sum of these three interior angles is 180 degrees, and sum of these three interior angles is also 180 degrees. So the sum of the interior angles of this quadrilateral also adds up to 360 degrees, right? Okay, therefore you can prove this statement is actually true. So this is an important property of any quadrilateral. The interior angles of any quadrilateral add up to 360 degrees. Then we can use this property to solve some of the questions. So for example, let's consider this quick quiz. In a quadrilateral ABCD, angle ABC are known. Sorry, angle AB are known and angle C is 30 degrees more than angle D. Can you find angle D? Again, I'll give you 2 minutes to solve this question. And then we'll have a look at the solution together. Okay, of course, when you finish, you can give me your answer in the chat box, okay? Alright, since most of you have already finished, let's have a look at the solution together. So we know that the sum of the angles in quadrilateral is 360 degrees, right? Therefore, we have angle A plus angle B plus angle C plus angle D is 360 degrees. This is a property of any quadrilateral, right? And angle C is 30 more than angle D. So we know angle A is 100 degrees, angle B is 50 degrees, and angle C can be written as angle D plus 3 degrees, then plus angle D, and then you will have a equation in terms of angle D, right? Which means angle D plus 150, then plus another 30, which gives us 180 degrees. So 2 of angle D plus 180 degrees equals 360 degrees. Therefore, angle D should equal 90 degrees, right? Did you get this correctly? No problem. Okay, so this is a basic property of the quadrilateral, which is true for any quadrilateral. So next, let's have a look at some different types of quadrilaterals. First is a trapezoid. Okay, first of all, the definition of trapezoid. A trapezoid is a quadrilateral that has at least one pair of parallel sides. So be careful with the keyword here, at least. So we have this diagram below is a typical diagram of a trapezoid, because in this diagram we have Wx is parallel to Zy, right? Also, the diagram on the right, as you can see here, this is a classification of different types of trapezoids. All of the trapezoids here have at least one pair of parallel sides, no matter whether the other pair of sides are parallel or not. Sometimes they are parallel. In that case, that could be a parallelogram, a rectangle, or square, or rhombus. So we'll talk about these later, okay? And sometimes the other pair of sides are not parallel. And usually when people talking about trapezoids, they're talking about cases where we have only one pair of parallel sides. But in fact, according to the definition, the rectangle, parallelogram, rhombus, and square can all be called trapezoids as well. But in this course, we'll focus on the cases where we only have one pair of parallel sides, okay? Which is shown here in this diagram. And these parallel sides are often called the bases of trapezoid, with the other sides called the legs. So these two sides are called bases. And the other pair of sides called the legs. The segment that connects the midpoint of the leg is called the median. MN here is a median of the trapezoid. In this case, MN is a median of trapezoid WXYZ. Okay, so have a look at these diagrams, and next let's have a look at the main properties of trapezoids. Okay, I'll give you some time to have a look at these diagrams first. Any questions, just let me know, okay? Alright, if you don't have any questions, let's have a look at an example here. So, suppose we have a trapezoid EFGH here. EF is parallel to GH, and EF is 6. The length of FG is 10. GH is, sorry, FG is 10. So this side is 10, and GH is 12. EH is 8. Can you find the length of the median MN? Okay, again, I'll give you 3 minutes to have a look at that. And if you finish, you can give me your answer in the chat box, okay? Okay, have you finished? Alright, then let's have a look at the solution together. Okay, so let's suppose the extensions of the legs meet at a point x. So this is the original trapezoid. And because EF is shorter than HG, we know that they will meet somewhere here, right? So let's call this point X. So first we can state that the extensions of the legs meet at a point X, and we can easily see that triangle EXF is similar to triangle HXG, right? According to AA similarity, because EF is parallel to HG, right? Therefore, we have XE over XH equals EF over GH, right? And we can substitute XH using XE plus 8. And solving this equation will give us 2xe equals xe plus 8, which means xe is 8, right? And similarly, we know xf over xg is 1 over 2. F is the midpoint of xg. Therefore, we have xf equals fg, which is 10. And also, m is the midpoint of fg, right? Therefore, we have xm equals xf plus fg over 2, which gives us 15. And similarly, we have xn equals 12, right? Since xn over xe equals 12 over 8, which equals 3 over 2, and xm over xf equals 15 over 10, which is 3 over 2, we have triangle XEF is similar to triangle XNM by SAS similarity, right? Therefore, we know that NM over EF equals XN over XE, which gives us 3 over 2, right? Therefore, we know we can find NM is actually 3 over 2 times EF, which is 3 over 2 times 6, which gives us 9, right? So the correct solution is 9. And also we have another conclusion, because angle XNM equals angle XEF. We also have NM is parallel to segment EF, right? Therefore, we have proved two things. First, EF is 6, HG is 12. We have proved that MN is just 1/2 of the sum of the two sides, EF and HG, right? Which is 9. And also we have proved that the median NM is parallel to the two sides, EF and HG. Therefore, this is an important property of the trapezoid. The median of a trapezoid is parallel to the basis of a trapezoid and equal in length to the average of the length of the basis. So in this diagram, suppose the two bases are A and B, median is M, then we know the median at N is parallel to both the two bases, and also we have M equals 1/2 of the sum of A and B. Alright, because we haven't learned how to calculate the area of a trapezoid, right? So let's have a look at this question first. This example will illustrate how we can calculate the area of a trapezoid. So bases PQ and SR have lengths 5 and 9 respectively, and are 8 units apart. What is the area of the trapezoid PQRS? Okay, I'll give you 1 minute to consider this question, and after that we'll have a look at the solution together, okay?
What does it mean they're 8 units apart? Does it mean like the height?
The distance between the two parallel lines is 8. You understand?
Like the shortest distance?
Yes, the shortest distance. Also, the height, yes, you're right, the height of that trapezoid is 8. Alright, let's have a look at the solution here. So, as I told you, we haven't learned how to calculate the area of a trapezoid yet, right? But we do know how to find the area of a triangle. So we can use the formula to find the area of a triangle to help us to find the area of a trapezoid. So we have two bases, 5 and 9, right? And these two sides are 8 units apart, which means we have a height of this trapezoid, which is 8. So we can divide the trapezoid into two triangles by drawing diagonal QS. We can connect Q and S. Then we have two triangles, right? PQS and QSR. Again, we can draw the height of the triangle PQS from point S, which is, the height is 8, right? You know the altitudes QS and SY of the two triangles are both 8, since the parallel lines are 8 units apart. So we have QX equals SY equals 8. Then we can now find the area of the trapezoid by adding the areas of the triangles. So area of PQRS is the sum of the area of triangle PQS plus area of the triangle QRS. which is 1/2 of PQ times SY plus 1/2 of SR times QX, right? And this gives us 8 times half of PQ plus SR. Let's call this point Y and call this point X. Okay, let this height be H, then we have 1/2 of PQ times H plus 1/2 of SR times H, which gives us 1/2 of PQ plus SR then times H, and this number is 56, right? So the area of this trapezoid is 56, and also you can see that the method we can use to calculate area of the trapezoid is here, which is 1/2 of the sum of the two bases times its height, right? Okay, therefore, this is another important property of a trapezoid. Area of a trapezoid equals the height of the trapezoid times the length of the median of the trapezoid, because we know 1/2 of the two bases is the median M. Then the area of WXYZ here of the trapezoid equals 1/2 of sum of A and B, which is M, times its height, H. Did you get it? So please write this down on your notebook, and we could use this to solve some related questions later, okay?
I don't understand why the area, what MH. Oh, okay, I see.
We have just proved this previously, right? M is a median, which means WM equals MZ, XN equals NY, right? If M is a median, then M equals 1/2 of A plus B, right? We have already proved this previously in the previous example, right? Can you follow me?
Yes.
Okay. Therefore, we have this property here. Okay, have you finished? Then we can have a look at another example here. Okay, so first of all, we can draw a diagram to illustrate the situation here. We have WXYZ, where WX equals 17, XY equals 13, YZ equals 21, and XZ equals 20, right? And we need to find the area of WXYZ. So usually, if you want to find the area of a trapezoid, you need the height and two bases. So here we have two bases, and we need the height, right? So we can try to add the height to the diagram in the way that forms useful right triangles here. So let's call this point is H. Then the altitude from X to XY is the most as X. The altitude from X is XH, right? And suppose XH equals H, and also we can let this side be X, and of course ZH would be 21 minus X, right? So first of all, we can have x squared plus h squared. In the right triangle xhy, we have 13 squared, which is 169, right? And consider the other right triangle xzh, we have 21 minus x squared plus h squared equals 20 squared, which is 400, right? So basically, we have two equations and two unknown quantities in which we can solve x and h. We can subtract the first equation from the second, which gives us 21 minus x squared plus h squared minus x squared plus h squared equals 400 minus 169. And this gives us, we can expand everything. This gives us 2, 3, 1, and then cancel x here. Oh, sorry, I lost a plus h here, right? H squared cancel this h squared, so 42x equals 210, right? And this gives us x equals 5. And let's call this number 3. Then we can put number 3 back into equation number 1. And h should equal 12, right? You follow me? So if the height is 12, then we know the area of wxyz, according to the formula, is 1/2 of wx plus zy and times the height h, right? Which is 1/2 of 17 plus 21 times 12. And this is 6 times 38. Which is 228, right? Any questions? Alright, if no questions, let's consider another practice. In the trapezoid ABCD, we have AD is parallel to BC, angle B equals angle C, and angle B is less than 90 degrees. Can you prove that AB is actually equal to CD? Okay, first of all, I'll help you to draw the diagram here. So A, B, C, D is the trapezoid. AD is parallel to BC. Angle B here equals angle C. Can you prove AB equals CD? Alright, have you finished? Okay, so once again, we can consider using the right triangles. We can introduce some right triangles to help us, right? So we can draw altitudes from point A and point D. So we draw altitudes of trapezoid A, B, C, D from A and D. So let's call these 2 points X and Y. Then we have AX should equal DY, right? Because both of them are heights or altitudes of the trapezoid. And because AD is parallel to BC, then we have triangle ABX must be congruent to triangle DCY, right? By which theorem should we use here? AAS, right? You see that? Therefore, we have AB equals CD, right? And also notice that we can easily deal with the cases of angle B and angle C being obtuse by noting that if angle B equals angle C, then we have angle A equals 180 degrees minus angle B, which equals 180 degrees minus angle C, which is angle D, right? So no matter angle B and angle C are obtuse or acute, we can always prove that AB equals CD, right? And again, this is another important property of a trapezoid. So two angles of a trapezoid that share one of the bases of the trapezoid as a side are together called base angles of the trapezoid. A trapezoid in which two base angles are equal is called an isosceles trapezoid, which is similar to isosceles triangles, but this time we have a quadrilateral trapezoid. So if the two base angles are equal, then we have an isosceles trapezoid. And isosceles trapezoid has the following important properties. In an isosceles trapezoid, first, the base angles come in two pairs of equal angles as shown at right. A equals D, B equals C. Second, the legs are equal, AB equals CD. And third, the diagonals are also equal, so BD equals AC in this case. You get it? And actually, if any of these items is true for a trapezoid with exactly one pair of parallel sides, then all the others must be true for that trapezoid. Did you get it? And actually, you can try to prove that the reverse statement is also true. So please write this down on your notebook. This is another important property of a trapezoid. Okay, have you finished? Okay, let's summarize what we have learned so far. So we have learned the definition of a quadrilateral, and then we have learned a special type of quadrilateral, which is a trapezoid. And we have talked about three important properties of a trapezoid. First, the median is 1/2 of the two bases, which is also parallel to the two bases, right? For the second property, we have the area of a trapezoid is 1/2 of the sum of the two bases times the altitude. And then the third property states that once you have an isosceles trapezoid, then you have the following properties, right? And if any one of these items is true for trapezoid, then you can prove that trapezoid is actually isosceles trapezoid. Then you have the remaining two properties, right? Okay, so let's consider one last example for the trapezoid, then we can take a 10 minutes break. So let's do this quick quiz here. Can you find Hj given that Ghij is isosceles trapezoid with Gh equals 8, Hi equals Gh equals 6, and Ij equals 10? Okay, again, if you finish, you can give me your answer in the chat box. GH is a shorter base and IJ is a longer base. Alright, if you finish, let's have a look at the solution together. Again, we have a isosceles tripezoid GHIJ, right? And GH is shorter, which is 8, and IJ is longer, which is 10. And we also know HI is 6, GJ is also 6. You need to find the diagonal HJ. Okay, so in order to find HJ, we can, well, probably find another right triangle to help us, right? We can start by drawing altitudes GY and HX. Okay, then we could consider these two right triangles. These two right triangles must be congruent, right? Why is that? Because this side equals this side, both are the altitudes of the trapezoid, right? This side equals this side, and they also have this angle equals this angle equals this angle, and that means this angle also equals this angle, right? Again, I'm not gonna write all of that. So we know that according to the discussion, then we have triangle GYJ must be congruent to triangle H, oh, this point is X, HXI, right? According to SAS, right? And therefore we know JY must equal XI, right? This side equals this side, right? And also because GY is parallel to HX, so XY is the distance between these two parallel lines, which is also 8, right? And that means JY equals XI, which equals JI minus GH over 2, right? We know IJ or JI equals 10, GH equals 8, divided by 2 gives us 1, right? This side is 1, this side is also 1. And then we consider in right triangle, let's consider right triangle HIX. Well, of course we can find HX here, right? HX is, well, HX square is HI square minus XI square, which is 36 minus 1, which is 35, right? And then let's consider right triangle HXY again as well. So in right triangle HXY, oh sorry, HXJ. Sorry about that. H should be HXJ, right? In this right triangle, we know HJ is the length we want to know, right? And we can use HX and XJ to find it. HX equals, well, HX square equals 35. Actually, we only need HX square, right? And also JX equals YX plus YJ, which gives us 11, right? Therefore, we know HJ square should equal, well, this HJ is a hypotenuse, right? Should equal HX square plus XJ square, which gives us 35 plus 121, which is 156, right? And therefore we know the length of HJ is square root of 156. And that's actually 2 square root 29, right? Oh, sorry, let me check. Calculation might be wrong here. This is not 121. This should be 9, right? Sorry about that. Okay, yx is 8, not 10. So we have 9 here. So that's 35 plus 81, which is 116. And square root of 116 is 2 times square root 29, right? So this is our final solution. Any questions? Alright, if you don't have any questions, let's take a 10 minutes break. And after that, we'll have a look at the definition and properties of parallelogram and ground bind. Okay, next let's have a look at the concept of parallelograms. A quadrilateral is called a parallelogram if both pairs of opposite sides are parallel. So in this diagram, if we have AB is parallel to CD, AD is parallel to BC, then this quadrilateral can be called a parallelogram. You see the difference between a parallelogram and a trapezoid? In trapezoid, we can only we have if a quadrilateral that has at least one pair of parallel sides, then it's a trapezoid, right? Then if a quadrilateral has both pairs of opposite sides are parallel, then it can be called a parallelogram, right? Okay, then next let's have a look at the property of parallelograms. In parallelogram ABCD as below, the opposite sides are equal, the opposite angles are equal, and the diagonals bisect each other. So can you actually prove this by yourself? Suppose AB is parallel to CD, AD is parallel to BC. First, can you prove that the opposite sides are equal? Okay, let's go to question 1. Second, question B, can you prove the opposite angles are equal? And C, can you prove that the diagonals bisect each other? Okay, I'll give you 2 minutes to think about the question by yourself, and then we can have a look at the solution together, okay? Alright, have you finished? Okay, let's have a look at question A first. Well, if you want to prove the opposite sides are equal, two equal sides, probably you can use some congruent triangles, right? For example, we can connect AC then because we have AB is parallel to CD, then we have angle CAB equals angle ACD, right? Also, because AD is parallel to BC, then we have this angle here equals this angle here, right? And also because they share the same length, AC equals AC, then we have triangle ABC is actually congruent to triangle Okay, so what are the corresponding vertices?
Is it a question for us?
Yes?
CDA.
CDA?
Yeah.
Yes, according to A S A congruency, right? And therefore the corresponding sides are equal, so A have AB equals CD, and also BC equals DA, right? Okay, that proves the first property. If we have a parallelogram ABCD, AB is parallel to CD, AD is parallel to BC, then we have the opposite sides must be equal, right? Okay, next, how do we prove opposite angles are equal? This is also very easy, right? Because we have triangle ABC is congruent to triangle CDA, we have already proved this, therefore we have angle B must equal angle D, right? So we have proved angle B equals angle D. And we also have, well, so let's call this equation number 1 and 2. If you add equation number 1 and 2, then you will have the other pair of equal angles, right? So this means angle CAB plus angle DAC is angle DAB, right? Angle ACD plus angle BCA is angle BCD. Therefore, we have proved the opposite angles are also equal, right? Okay, so how about the next one? The diagonals bisect each other. Okay, then we should connect B and D, right? We need to prove BD and AC bisect each other. How do we prove this? Well, actually, you have already proved that this angle equals this angle, right? This angle equals this angle, right? You also prove this side AB equals this side. Therefore, this triangle, well, let's call this point O. This triangle AOB must be congruent to triangle COD, right? So because of the discussion, I'm not gonna write all of these. Therefore we have triangle AOB must be congruent to triangle COD, right? By ASA congruence. Therefore we have corresponding sides are equal, so AO equals CO, right? And also BO equals DO. Therefore we have diagonals bisect each other. Can you see that? Okay, so this is one important property of the parallelogram ABCD. Okay, please write this down in your notebook. And the question is the reverse statement is also true? Well, actually, the reverse statement is also true. Suppose ABCD is a parallel. Conversely, ABCD is a parallelogram if any one of the following are true, which means if you have whether A or B or C here is true, you can also prove the quadrilateral ABCD is a parallelogram. Can you see that? Can you prove this by yourself? First, if you have AB equals CD and AD equals BC, can you prove ABCD is a parallelogram? Second, suppose you have angle A equals angle C and angle B equals angle D. Can you prove ABCD is a parallelogram? And last, suppose the diagonals AC and BD bisect each other. Can you prove ABCD is actually a parallelogram? Okay, I'll give you 2 minutes to think about this by yourself, and then we can have a look at the solution together, okay? Alright, have you finished? Okay, again we can make use of a pair of congruent triangles, right? We can connect AC. Then if we have AB equals CD and AD equals BC, then because of this we have triangle ABC must be congruent to triangle CDA, right? According to SSS, because they also share the same length AC. Therefore, we have this angle equals that angle here, right? And this angle equals this angle here. Angle CV equals angle DCA. And this gives us AB must be parallel to CD, right? And also angle ACB equals angle CAD, and this gives us AD is parallel to BC. Therefore, we have proved two pairs of parallel lines, and according to the definition of parallelogram, If both pairs of opposite sides are parallel, then we can call this quadrilateral a parallelogram, right? So we can actually prove the first one. You see that? How about the second one? If we have A equals C, if you have angle A equals angle C and B equals D, well, actually the method should be the same, right? We can make use of a pair of congruent triangles. A equals C, and B equals D. How do you prove ABCD is a parallelogram? Okay, first you can connect A and C as well, right? So, any ideas? Well, sorry, actually, you don't have to, because, well, if angle A equals angle C, angle B equals angle D, then we know angle A plus angle B must equal angle C plus angle D, right? Which is 360 degrees over 2, which is 180 degrees, right? So if angle A equals angle B equals 180 degrees, because angle A and angle B are the same side interior angles, so we can prove AD is actually parallel to BC, right? And if we can also have angle A plus angle D equals angle C plus angle B, which is also 360 degrees over 2, which is 180 degrees. This means AB is parallel to CD, right? So we can prove this is actually a parallelogram. You see that? Okay, and for the third one, if the diagonals AC and BD bisect each other, so let's draw the bisects first, which means this side equals this side equals this side. Can you prove AB is parallel to DC? Of course, this is also very easy, right? We can make use of these two triangles. The triangle ABO is congruent to triangle COD, right? Because this side equals this side equals this side, and they have a pair of vertical angles, right? Therefore, you can prove this angle equals this angle here. That means this line is AB is parallel to CD, right? And using the same method, you can also prove that triangle AOD is congruent to triangle BOC, which means this angle equals this angle here, which proves this side AD is parallel to side BC, right? Therefore, again, you have two pairs of opposite sides, and then the quadrilateral ABCD must be a parallelogram according to its definition, right? So this property is actually reversible. So let's make a summary here. In a parallelogram ABCD, the opposite sides are equal, the opposite angles are equal, and the diagonals bisect each other. And conversely, ABCD is a parallelogram is if any one of the following are true. Okay, be careful with the keyword here. Any one of the following. First, AB equals CD and AD equals BC, or angle A equals angle C and angle B equals angle D, or diagonals AC and BD bisect each other. Any questions? All right, then if you don't have any questions, let's have a look at another example. So here in this diagram, side EU and NT of parallelogram ENTU are 5 units apart as shown. EU is given as 12, EN is 8. A, can you find the area of parallelogram ENTU? B, how far apart are sides EN and TU? And be careful that we haven't learned any formulas to calculate the area of a parallelogram, right? So we can only make use of what we have learned so far. We learned how to calculate the area of a triangle, right? So probably we can connect ET or NU. Suppose we connect ET, then we know that the area of the parallelogram ENTU can be calculated by adding up the triangle area of triangle EUT and the area of the triangle ENT, right? And we know that the area of triangle EUT is 1/2 of the base, which is EU, times the height, which is the distance between EU and NT, right? Which is h. Of course, here h equals 5. Can you see that? And ENT is, area of ENT is 1/2 of NT, the base, times the height h, right? So that gives us 1/2 of h, then times either EU EU plus NT, right? No, actually EU plus NT, because EU equals NT, right? This is a parallelogram, so opposite side should be equal. So therefore we have 1/2 of h times 2NT, which gives us actually NT times h. You see that? Which is 12 times 5, which is 60, right? And if you know the area of the parallelogram ENTU, then it's very easy to find the distance between EN and TU. So as you can see here, the area of the parallelogram can be given by the base times its height, right? Therefore, if you are using if you are using UT as EN as the base, then you should multiply this by the corresponding height. So let's call the height here as h1. This is a distance between EN and TU, right? And that gives us 60. Therefore, we know the distance you are looking for, which is h1, equals 60 over EN, which is 8. And this gives us 15 over 2, which is 7.5. Did you get it? Any questions here? So this actually gives us a method to calculate the area of a parallelogram, which is its base times its height. Suppose we have parallelogram as shown on the right, ABCD. Then the area of ABCD can be calculated using AB times XY or BC times PQ. XY and PQ are the corresponding heights. Okay, and this is another important property of a parallelogram. Please write it down on your notebook, okay? Have we finished? Alright, then let's have a look at another type of quadrilateral, which is called rhombi. Actually, rhombi is a plural form of the word rhombus. A quadrilateral is a rhombus if all of its sides are equal. So suppose we have a diagram here. If AB equals BC equals CD equals DA, then this quadrilateral is called a rhombus. Also note that if AD equals BC and AB equals CD, we can prove this is actually a parallelogram, right? So every rhombus is also a parallelogram. Therefore, all that is true about parallelograms is also true about rhombi. Did you get it? Okay, then let's have a look at a special property of a rhombus according to this introductory example here. Suppose ABCD is a rhombus such that its diagonals AC and BD have lengths AC equals 30 and BD equals 16. Can you find AB and AB? Can you find length of AB and area of ABCD? Alright, have you finished? Any ideas? Okay, first let's draw a rhombus first. So a rhombus is also a parallelogram, right? And actually the four sides are all equal. So AB equals BC equals CD equals AD, right? And we know the length of the two diagonals, so let's connect the opposite vertices. Let's call this point X here. Okay, all four sides of rhombus ABCD are equal, and that diagonals bisect each other, right? Because the rhombus is also parallelogram. For a parallelogram, the diagonals bisect each other. Therefore, we have bx equals xd, right? ax equals xc. Can you see that? Therefore, because of this, I'm not going to write all of this. But because of the discussion here, we have triangle ABX must be congruent to triangle CBX, which is also congruent to triangle CDX and congruent to triangle ADX, right? All of the four little triangles are congruent. Also, this angle equals this angle equals this angle equals this angle, which is a quarter of 160 degrees, right? Therefore, we have BX is also perpendicular to AC, right? And therefore, we know the area of ABX can be given as 1/2 of BX and AX, right? Because BX is perpendicular to AX. And that is 1/2 of BX. BX is 1/2 of BD, right? Which is 8 times AX is 1/2 of AC, which is 15. So that means the area of ABX is 60, right? And therefore we have the area of ABCD is 4 times the area of the little triangle ABX, which is 4 by 60, which gives us 240, right? And then AB is square root of bx squared plus ax squared, right? Which is square root of bx is 1/2 of bd, which is 8. Ax is 15. So that is square root of 64 plus 225, which gives us square root of 289, which is 17, right? Did you get it? And also note that the area of ABCD is actually can be represented by twice of AX times BX, right? Because this is actually 2 of AC over 2 times BD over 2, which is 1/2 of AC times BD, right? So this is another important property of the special parallelogram rhombus. So let's make a summary here. The diagonals of a rhombus are perpendicular. The area of a rhombus is half the product of its diagonals. Of course, it's also base times height, since the rhombus is also a parallelogram. You see that? So suppose you have a rhombus here. The area of rhombus ABCD is given by 1/2 of AC times BD. Okay, please write this down in your notebook. Alright, now let's have a look at topic 8, quadrilaterals part B. So previously we have talked about the concept of quadrilateral basics, trapezoids, parallelograms, rhombi. And today in part B, we're going to have a look at the concept of rectangles, squares, and the statement if and only if, and together with some other quadrilateral problems. Okay, first of all, the concept of rectangles. A rectangle is a quadrilateral with 4 right angles. So by the definition here, you can see every rectangle is actually also a parallelogram, right? Therefore, all that is true about parallelograms is also true about rectangle. All the properties you learned in the parallelogram section also applies to rectangles. Okay, and there are some special properties for rectangles. And next, let's have a look at an example here. And this will illustrate some special properties a rectangle has. So find the length of a diagonal of a rectangle given that its perimeter is 44 and one side has length 10. Okay, first of all, I'll give you 3 minutes to have a look at this question by yourself, and then we're going to have a look at solution together. Okay. All right, have you finished? Okay, let's have a look at the solution together. First of all, let's draw the diagram to illustrate the situation here. So we draw a rectangle. Suppose our rectangle is W, X, Y, Z. So let W, X, Y, Z be our rectangle. And let XY be 10 because it says one side is 10, right? We note that the diagonals have the same length, so we don't have to worry about which diagonal to find. Since xy equals 10, we have wz is also 10, right? And because the parameter is 44, then we have wx plus xy plus yz plus zw equals 44. So because we have wx equals yz and xy also equals wz, right? Equals 10. Then we have wx equals yz equals 12, right? And now we can find the diagonal now. So this side is 10 and this side is 12. Then in right triangle xyz, we have xz equals square root of xy square plus yz square, which gives us 10 square plus 12 square, which is 2 square root of 61, right? Therefore, the diagonal of this rectangle is 2 square root 61. Did you get it? Any questions? Okay, so that tells one thing about the property of a rectangle. Diagonals of a rectangle are equal to each other. You can actually prove this by using congruent triangles, right? And equal to the square root of the sum of the squares of the length and the width of the rectangle. For example, if we have a rectangle PQRS, then we know the diagonals QS equals PR. PR equals square root of QR square plus SR square. Okay, have a look at the property here. Let me know if you have any questions, okay? Alright, if you don't have any questions, now let's have a look at another special quadrilateral, which is squares. A square is a rectangle, a square is a regular quadrilateral, which means that it has 4 sides of equal lengths and 4 equal angles, 90 degrees angle or right angles. It can also be defined as a rectangle with 2 equal lengths adjacent sides. So a square is a special rectangle, right? A rectangle is a special parallelogram. And one important property regarding the square is, suppose we have a square ABCD here. If you let S be the side length of a square, P be the perimeter, then and A be the area, then we have P equals 4S, right? Because we have 4 equal sides, and A equals S squared, because the sum of the 2 right triangles, which is 2 times 1 over 2S squared, which is S squared, right? Okay, sorry about that. And drawing a diagonal creates 2 45, 45, 90 triangles. Letting the length of a diagonal be D, then we also have the following conclusions. D equals S times square root 2, and P equals D times 2 times square root 2, and A equals D squared over 2. Okay, have a look at the property here, and let me know if you have any questions. Try to prove each of them by yourself, okay? So why the last one is true? Because a square is actually also a rhombus, right? And the area of a rhombus tells us the area equals 1/2 of the product of the two diagonals. So that's 1/2 times d times another d, which is 1/2 of d squared, right? Okay, have you finished? Alright, so now you should be very clear with the relationships of the perimeter, area, side length, and the diagonal of a square, okay? And now let's consider this question here. Suppose we have a square ABCD. The circle with center A and radius AB meets the perpendicular bisector of segment AD in 2 points, of which O is the one inside the square. Can you find the angle AOC? Okay, I'll give you 5 minutes to consider this question by yourself, okay? And after that, we'll have a look at the solution together. Alright, if you finish, please give me your answer in the chat box. Alright, let's have a look at the solution together. So there doesn't seem any easy way to get angle AOC directly, right? So we can try splitting it into pieces by drawing AD. We can connect point O and D, right? So in this way, because this side equals, well, this triangle is congruent to this triangle, right? Can you see that? Because this side equals this side, and this angle is 90 degrees, this angle equals 90 degrees, and they share the same side here. Therefore, we know triangle AOY is congruent to triangle DOY. Therefore, this side equals this side, AO equals OD, right? And because AO is also equals AB, which equals AD, so we have a equilateral triangle AOD. Therefore, this angle must be 60 degrees, right? Can you see that? And then, as long as you can find this angle here, then you can find angle AOC, right? Also note that OD is actually equal AO, which equals AB, which also equals CD, right? Therefore, triangle CDX is actually a isosceles triangle. So we know that this angle here equals 90 degrees minus 60 degrees equals 30 degrees, right? Therefore, we have angle DOC equals angle DCO, which is 180 minus 30 over 2, which is 75, right? Therefore, the angle you're looking for is 60 plus 75, which is 135 degrees. Did you get it? So, according to our analysis, you can write the answer like this. So first of all, we can draw segment OD, right? And because of something, I'm not gonna write all of the statements here, okay? And then we have triangle AYO is congruent to triangle DYO by SAS, right? Therefore, we have AO equals OD equals AB equals AD, right? Therefore, we know angle DAO equals angle AOD equals angle ODA equals 60 degrees, right? And next, because OD equals AO equals AB equals CD, therefore OD equals CD, right? Then we know angle DOC equals angle DCO. And we also know angle angle ODC equals 90 degrees minus angle ADO, which is angle ADO is 60 degrees as well, right? Which is 30 degrees. Therefore, we know angle DOC equals angle DCO equals 1/2 of 180 minus 30, which is 75 degrees. Therefore, the desired angle AOC equals angle AOD plus angle DOC, which is 60 degrees plus 75 degrees, which equals 135 degrees, right? You get it? Any questions? Okay, if no questions, let's have a look at a special statement in geometry. We have learned a lot of statement contains this statement, if and only if, right? So what does really means? What does this really mean? Many mathematical statements put if and only if together. here's what it looks like in a non-mathematical context. Let's consider this context first. A month has fewer than 30 days if and only if the month is a February. So it has two meanings actually. This statement is equivalent to say both of the following statements at the same time. First of all, every month with fewer than 30 days is February, which is this direction, right? The month has fewer than 30 days. That indicates the month is February. Second, every February has fewer than 30 days, which is from this direction, right? If we know a month is February, then that month has fewer than 30 days, right? And actually, we can combine these two signs using just one bidirectional sign like this. And this is read as if and only if. Did you get it? So if and only if is actually bidirectional statement. You could either from left to right or from right to left. Each direction is true. And that means proving if and only if statements requires proving two different statements, both from left to right and from right to left. The statement and the reverse statement must also be true, must be both true in order to say if and only if. Okay? And sometimes the phrase if and only if is shortened to IFF. So IFF in mathematics means if and only if. For another example, we could say that x squared equals 4 if and only if x equals either positive or negative 2, right? Because if you have x squared equals 4, we can have x is either positive 2 or negative 2, right? And at the same time, if we have x equals either positive or negative 2, we can have x squared equals 4, right? You can infer either from left to right or from right to left. Both of the two statements are true. Therefore, we can say x squared equals 4 if and only if x equals either positive or negative 2. Did you get it? So this sign here actually means equivalent. So the statement on the left side and statement on the right side are actually equivalent statement. They are actually the same thing, right? Okay, so now let's have a look at an example. So can you prove that ABCD is a parallelogram if and only if angle A equals angle C and angle B equals angle D? Okay, so according to the meaning of if and only if, we need to prove two statements, right? First of all, we must prove ABCD is a parallelogram if angle A equals angle C and angle B equals angle D. Or you could also say from angle A equals angle C and angle B equals angle D, we could infer that ABCD is a parallelogram, right? So how do you prove this? Since angles of a quadrilateral adds to 360 degrees, right? We have, okay, let's show proof here. We know that angle A plus angle B plus angle C plus angle D equals 360 degrees. And because angle A equals angle C, angle B equals angle D, then we have twice of angle A plus angle B equals 360 degrees. Therefore, angle A plus angle B equals 180 degrees, right? Therefore, AD is parallel to BC, right? And similarly, we have twice of angle A. We're going to use angle B and angle C. Twice of angle B plus angle C equals 360 degrees. Therefore, we know angle B plus angle C equals 180 degrees, right? Same side interior angles add up to 180 degrees. That means AB is parallel to DC as well, right? Therefore, we know ABCD is a parallelogram. Because according to definition, two pairs of the opposite side are parallel. So two pairs of the opposite side are parallel, then that quadrilateral is a parallelogram, right? So we have proved the first statement. If angle A equals angle B and angle B equals angle D, then ABCD is a parallelogram. So second, you must also prove that if ABCD is a parallelogram, we have angle A must equal angle C, and of course we also have angle B equals angle D. So can you prove this by yourself? Okay, so we can start by saying because AB is parallel to DC. This time, because ABCD is already parallelogram, right? This is our starting point. Because AB is parallel to CD, then we have angle A plus angle D equals 180 degrees, right? And because AD is also parallel to BC, then we have angle A plus angle B equals 180 degrees, right? Therefore, we know angle D must equal angle B, right? So we have proved angle B equals angle D. And you can use similar method to prove angle A equals angle C, right? Did you get it? Therefore, we have proved both directions. First of all, if ABCD is a parallelogram, then we have angle A equals angle C, and angle B equals angle D. The reverse statement is also true, because if we have angle C equals angle A, and angle B equals angle D, then we can prove ABCD is a parallelogram. Then we can say ABCD is a parallelogram if and only if, and sometimes you could also use this notation. This sign means if and only if A equals C and B equals D. Did you get it? This is the meaning of if and only if, okay? Okay, here I'll give you a quiz. Please write this question down on your notebook and try to solve this by yourself after this class, okay? see if you can prove that diagonals of a trapezoid are congruent if and only if the trapezoid is isosceles. Okay, have you written this down? Okay, and probably we'll have a look at the solution in our next lesson. Okay, I'll leave this to your homework. Let's have a look at the summary of the types of simple quadrilaterals. Okay, so we have learned that of all the simple quadrilaterals, we can have concave quadrilaterals, which are not the objects we are studying in this course. And some of the quadrilaterals are convex quadrilateral, right? Of the convex quadrilaterals, we could have some quadrilaterals are trapezoid, right? And some trapezoid are parallelograms. Some parallelograms are rectangles, and some rectangles are squares if some special conditions are met, right? And of course, some parallelogram are also rhombus. And there are some overlapped area between rhombus and rectangles. And that ones are called squares, right? Okay, the objects we haven't talked about are kites. Note that a kite is a quadrilateral with reflection symmetry across one of its diagonals. So a kite is not a parallelogram. Well, a kite is not necessarily parallelogram, right? Or a kite is not necessarily a trapezoid either. Okay, careful with that. And equivalently, it's a quadrilateral whose four sides can be grouped into two pairs of adjacent equivalent sides. Okay, any questions? All right, then let's have a look at some exercise questions, which summarizes what we have learned in this topic. Okay, have a look at the question here. Diagonal BD of a square ABCD is drawn here. Square EFGH is then inscribed in triangle BDC with two vertices on BD as shown here. If AB is 6, can you find the area of EFGH? Okay, if you finish, please give me your answer in the chat box, okay? Alright, since some of you have already done it, let's have a look at the solution together, okay? So if you want to find the area of EFGH, if we know the side of that square, then we know the area, right? So we could let the side length of square EFGH be x, then we need to solve x first, right? Since triangle EBF is 45, 45, 90 triangle, right? Because we know this angle is 45 degrees, this angle is also 45 degrees, right? You see that? Because ABD is congruent to triangle BCD, therefore both of these two angles are 55 degrees. 45 degrees. So say because triangle EBF is 45, 90, 45, 45, 90 right triangle, then we have BF equals EF times square root 2, right? Which gives us x times square root 2. You get it? We also have BE equals EF equals x, right? And because BD is parallel to FG, we have angle FGC equals 45 degrees as well, right? So triangle FCG is also a 45, 45, 90 right triangle, right? Therefore, we have FC equals FG over square root 2, which equals x over square root 2, which equals x times square root 2 over 2, right? We know that BC is 6. Therefore, we have BF plus FC equals BC equals 6. Then substitution can give us x square root 2 plus x times square root 2 over 2 equals 6, right? Therefore, we know x times 3 square root 2 over 2 equals 6. Solve this equation gives us x equals 2 square root 2. Did you get it? Therefore, we know the area of EFGH is simply x squared, which gives us 8. Did you get it? Any questions? Thanks for the answer. Alright, if you don't have any questions, let's consider the next one. I have a rectangular painting that has a length 10 inches longer than its width. I frame it with a rectangular frame that is 2 inches wide all the way around. Given that the area of the frame is 152 square inches, what is the area of the painting? Okay, again, I'll give you 3 minutes to think about this question by yourself. Probably drawing a diagram will help you think this question. So you could start by making a sketch of the painting with this frame. Alright, again, if you finish, please give me your answer in the chat box. Okay, let's have a look at the solution together. Okay, first of all, let's sketch the diagram of this question here. We can, well, first of all, we have a painting, right? And it says the length is 10 inches longer than its width. So we could let the width be x, then the length must be x plus 10, right? And you have a frame outside of the painting. Well, let's draw a frame of that painting here. It says rectangular frame with 2 inches wide all the way around. That means this length is 2, right? And this length is also 2 inches here and 2 inches here. X is this length. Alright, next. What else do we have? We have okay, so if this side is x plus 10, then we know this side must be x plus 10 plus 2 plus another 2, which is basically x plus 14, right? And we also know this side is x plus 2 plus another 2, which is x plus 4, right? And according to the given information, we know that the area of the rectangle of that frame subtracted by the area of the painting, the difference is 152 square inches, right? So that means we have x plus 14 times x plus 4 minus x times x plus 10 equals 152, right? And basically you have an equation in terms of x, which you could solve x, right? Well, this means x squared plus 18x plus 56 minus x squared minus 10x equals 152. And we can solve this equation to get x is actually 12. The unit is inches, right? And therefore we know the area of the painting without the frame is x times x plus 10, which is 12 times 22, which is 264 square inches. You get it? So you could say the area of the painting without frame is 264 square inches. Do you get it? Okay, have a look at the solution here. Any questions, just let me know, okay? Alright, if you have finished, let's consider one last question, then we can end this class. So, as shown on the right, given ABCD is a parallelogram, can you prove that AC squared plus BD squared equals AB squared plus BC squared plus CE squared plus DA squared? Which means the sum of the squares of the diagonals of parallelogram equals the sum of the squares of the sides of the parallelograms. Okay, I'll give you 5 minutes to try to prove this by yourself, okay? and then we'll have a look at the solution together. So actually, you can consider this as another property of the parallelogram if you can prove this, right? Okay, have you finished? Alright, now let's have a look at the solution together. So note that if you have a parallelogram, then we have AB must equal CD and AD equals BC, right? So if you want to prove AC squared plus BD squared equals BD squared plus BC squared plus CD squared plus DA squared, then that actually can be inferred from AC squared plus BD squared equals, because AB equals CD, so as long as you can prove equals twice of AD squared plus CD squared, if you can prove this, then you can prove this, right? So our target becomes the statement here. If you can prove AC squared plus BD squared equals twice of AD squared plus CD squared, then of course we can prove this, right? Because AD equals BC and AB equals CD. Then we can draw altitudes from A and B. So let's call these 2 points P and Q. Thus building right triangles with our diagonals as hypotenuses, right? So from right triangles APC and right triangle BQD. we have AC squared equals PC squared plus AP squared, and BD squared equals DQ squared plus BQ squared, right? And we can add these to get expression from the sum of the squares of the diagonals. So AC squared plus BD squared then equals, the right side is just PC squared plus AP squared plus DQ squared plus BQ squared, right? And start by noting that DQ equals CD plus CQ, right? And PC equals CD minus DP. We also note that AP equals BQ and AD equals BC, right? So we have triangle ADP must be congruent to triangle BCQ by the HR congruence, right? Thus we have DP equals CQ. Now our equation becomes AC squared plus BD squared equals PC squared plus AP squared. Okay, that involves some algebraic expressions, transformations there. So that be transformed to CD minus DP squared, right? Plus AP squared, then plus CD plus CQ squared, then plus BQ squared, right? And let's expand and simplify. This gives us CD squared minus 2CD times DP, then plus DP squared plus AP squared plus CD squared plus 2CD times CQ, and plus CQ squared plus BQ squared. And that can be simplified to CD squared minus 2CD DP plus DP squared plus AP squared plus CD squared, then plus 2CD DP plus DP squared plus AP squared, right? Which can be simplified to 2CD squared plus 2DP squared plus AP squared, right? And I'll write it here on top. Since we have DB squared plus AP squared equals AD squared, right? From the right triangle, DAP. Then we have the desired statement, which is AC squared plus BD squared equals this one equals that one, which is 2 times CD squared plus AD squared. Can you see that? And if you have proved this, that means you can prove this, right? If you prove this, because AD equals BC and CD equals AB, then of course you can prove this, right? Therefore, we have proved the desired statement here, which means the sum of the squares of the diagonals of a parallelogram equals the sum of the squares of the sides of the parallelogram. You can also consider this as a property of any parallelogram, okay? Alright, let's have a look at topic 9, polygons. So we have already tackled 3 sides, right? And we have already handled 4 sides. When you have 3 sides, usually we call them triangles, and when you have 4 sides, we call them quadrilaterals, right? So why we stop here? So as shown here, figure 9.1, There are several different polygons, which are closed planar figures with line segments as boundaries. So all of the names of the parts of a general polygon are actually the same in the polygons we have learned about so far. For example, triangles and quadrilaterals. The segments that form the boundary are sides, which meet at vertices to form the interior angles. If we connect two vertices that are not adjacent on the polygon, then we can form a diagonal, such as diagonal AC in this figure here. And polygons are classified by the number of sides they have. Here are some names given to different polygons. You can have a look at that. When the number of sides is 3, we call them triangle. When the number of sides are 4, we call them quadrilateral, and so on. Alright, then next let's have a look at the concept of regular polygon. A polygon in which all the sides are equal and all the angles are equal is called a regular polygon. Actually, we have already seen 2 examples of regular polygons, right? Equilateral triangles are regular polygon, and squares are also regular polygon who has 4 sides, right? So here, figure 9.3 shows a few more regular polygons. And as with quadrilaterals, we will be focusing on convex polygons in this lesson, unless otherwise stated. Can you recall the meaning of convex polygons? Okay, we'll only focus on the concept of convex polygons, and we'll discuss their properties in this lesson, unless otherwise stated. This means the interior angles of the polygons are all less than 180 degrees. Any questions? Alright, then first of all, let's have a look at the angles in a polygon. So in this lesson, we explore not only the interior angles of a polygon, but also the exterior angles. Exterior angles are formed by extending the sides of a polygon. For example, here in this diagram, angle BAX is an exterior angle of the polygon ABCDE. Okay, this is called an exterior angle. And all these angles are the interior angles of the polygon. Are you clear? Alright, so next let's have a look at an example which shows a property of the interior angles of a polygon. So can you find the sum of the measures of the interior angles of pentagon A, B, C, D, E? Without measuring the angles. Okay, when you finish, please give me your answer in the chat box, okay? Have you finished? Neil? Amber? Leo? If you finished, please give me an answer in the chat box. Yeah, that's a question. Why it's 540? How did you get that? We are trying to prove this rule, right? Alright, let's have a look at the solution together. So we don't know anything about the pentagons, right? But we know plenty about triangles. Therefore, we could use diagonals to cut the pentagon into some triangles, right? We could, for example, we could connect A and D, and then connect point A and C. Then we have triangle ADE, triangle ACD, and triangle ABC, right? We know the sum of the angles in the pentagon is the same as the sum of these angles. 1, 2, 3, 1, 2, 3, and 1, 2, 3, right? So here, sum of these three interior angles is 180 degrees. Sum of these three interior angles is 180 degrees. And sum of these interior angles is also 180 degrees. This is what we have known for triangles, right? Therefore, the sum of the interior angles in a pentagon is 3 times 180 degrees, which is 540 degrees, right? You get that? And based on this, can you find a formula for the sum of the interior angles of a convex polygon with n sides? Again, when you finish, could you give me your answer in the chat box? Alright, let's have a look at the solution. So as we did with the pentagon, we can actually break the polygon into triangles by drawing all the diagonals from one of the vertices, right? Sum of the angles in these triangles equals the sum of the angles in the polygon. Therefore, all we have to do is figure out how many triangles we can form when draw the diagonals. So for example, if you have a convex polygon, then suppose this is a point A. How many triangles can you have when we draw the diagonals? We could let A be the common vertex of all of our triangles. So each side of the polygon, except the two sides, which is this side and this side, right? Connected to A, is the side opposite A in exactly one of our triangles. So there must be n minus 2 triangles formed, right? You see that? By drawing the diagonals. Because if you don't count these two exceptions, there are n triangles, and actually we can't use these two sides, therefore there must be n minus 2 triangles, right? And since there are 180 degrees in each triangle, the sum of the angles in an n-gon is just 180 degrees times n minus 2, or 180 times n minus 2 degrees, right? So this is a general formula for the sum of the interior angles of a convex polygon with n sides. Well, again, this is not a rigorous proof, but the result also holds if you write the rigorous statements. And actually, it's a little more complex to prove that this is actually holds true for concave polygons as well. So this is also true for concave polygons. So we have just proved this is true for convex polygons, right? And we're not gonna show the proof for concave polygons If you are interested, you could just Google them by yourself, okay? And any questions, just let me know in our next class. Okay, so in a summary, we have the relationship between the sum of the interior angles and the number of sides for a n-sided polygon. Sum of the interior angles in a n-sided polygon is given by this formula, 180 times n minus 2 degrees. Therefore, the measure of each of the n interior angles in a regular n-gon is given by sum of the total angles divided by n, right? This is one of the most important property for the polygons. So have a look at the property here, and probably want to write this down. Alright, if you don't have any questions, let's have a look at another example. Now we turn our attention from the interior angles to the exterior angles. So let's have a look at this example here. The diagram on the right shows the 10 exterior angles of a decagon. Find the sum of these angles. Again, you could not just assume all the exterior angles have the same measure. And again, if you finish, please give me your answer in the chat box, okay? Okay, and actually this is also true when the side is n. For example, if the side is n, we know that the sum of the exterior angles plus the sum of the exterior angles should be n times 180 degrees, which is 180n, right? Then the sum of the exterior angles is n minus 2 times 180, which is 180n minus 360 degrees, right? Therefore, in that case, for n-gon, the sum of the exterior angles is just 180n minus 180n minus 360, which is also 360 degrees, right? For n-gon. Did you get it? Therefore, we know that for a n-gon, the sum of the exterior angles is always 360 degrees. And in a summary, sum of the exterior angles in a convex polygon with n sides is 360 degrees. And of course, the measure of each exterior angle in a regular n-gon is 360 degrees over n. You get it? So this is what we have known so far for the interior angles and exterior angles. So let's try using our new knowledge about the angles of polygons with a couple of example questions below. First, could you find the number of sides in a regular polygon in which each exterior angle measures 182 degrees? Have you finished number? Any ideas? Well, let's suppose the polygon have n size. Then there are two general approaches we can take to this problem. You could use either the interior angle or the exterior angle, right? We know that if you use the interior angle, we know the sum of the interior angles is, well, because each interior angle is 172 degrees, then the sum of the interior angles is 172 times n, right? And we also know we have a formula showing that the sum of the n exterior angles in a regular n-gon is 180 times n minus 2, right? So on the other hand, we have n minus 2 times 180 degrees here, right? Again, we have one equation, one unknown variable n, so we could solve n, which means 172n equals 180n minus 360 degrees, and 8n equals 360 degrees. Sorry, I should not write the unit here. And therefore n equals 45, right? And on the other hand, you could also focus on the exterior angle. So another method we could use is, since the measures of each interior angle is 182 degrees, each exterior angle is each exterior angle is just 180 degrees minus 172 degrees, which is 8 degrees, right? And we know that the sum of the exterior angles is 8. Times n, and this equals 360, right? And therefore you could also solve n equals 45. Did you get it, Amber? Okay, good. All right, have a look at the solution here. Any questions, just let me know, okay? All right, if you don't have any questions, let's consider the next one. So there is a regular 15 gon. Can you find angle ACB, ACD, and angle ADE? Again, I'll give you 3 minutes to consider this question, and after that, we'll have a look at the solution together, okay? And if you have finished, you can give me an answer in the chat box. Alright, let's take a 10-minute break, okay? After that, we can have a look at this question here. See you in 10 minutes. Alright, let's continue. Have you come back? Alright, so first let's draw a diagram to illustrate the concept here. And actually, we don't have to draw all sides. Because we only care about ACB, ACD, and ADE, right? So let's say this is AB, and then BC, then CD, and then DE. So we need to connect AC, connect AD, and since the polygon is a regular 5-gon, then each exterior angle is 360 over 15, which is 24 degrees, right? And each interior angle is 180 degrees minus 24 degrees, which is 156 degrees. And if you consider triangle ABC, this is actually a isosceles triangle, right? Angle BAC equals angle ACB. So we know the interior angle is 156 here, right? Therefore, we know each of the base angles should be 12 degrees because the sum of the three interior angles is 180, right? Therefore, we know angle BAC equals angle ACB, which is 12 degrees. That completes the first question. And then next, let's consider angle ACD. So angle ACD equals angle BCD minus angle ACB. We know angle BCD is 156 degrees minus angle ACB, which is 12, and that gives us 144 degrees, right? Okay, and in order to find angle ADE, we need to find this angle first, right? If you know this angle, then using the interior angle subtracted by angle ADC, then you will get angle ADE, right? So is it easy to find this angle? Well, we could use some congruent triangles to help us with that. So if you connect B and D, then we know triangle ABC must be congruent. Triangle ABC must be congruent to triangle BCD, right? Because this side equals this side. This angle equals this angle. Both of them are just interior angles of the 15-gon, right? And this side just share the same side here, right? You follow me? Therefore, these two triangles are congruent. Then we know that this angle here is also 12, right? And this angle here is 12. And then this angle here must be 24. And here this angle is 156. And of course this angle here is 156 as well. And what else? We know this angle equals this angle, right? In the two congruent triangles, we have just oh, sorry. I think yes, because we have just proved triangle ABC is congruent to triangle BCD, right? Therefore, this side equals this side. Then they share the same side here, and this side equals this side. Then we can say triangle ABD is congruent to triangle ACD, right? Therefore, we could also prove this angle equals this angle here, right? Then we know both of them should be 12 as well. Then you can find angle ADC is actually 24, right? And then triangle ADE should equal the interior angle 156 minus 24, which is 132 degrees, right? Did you get it? Okay, so next we have seen all sorts of problems involving triangles and quadrilateral areas. You won't be at all surprised that we rely heavily on triangles and quadrilaterals when we find area of polygons with more size, which basically means we're going to have a look at the polygon area. For example, if we have a diagram shown here, can you find the area of pentagon ABCDE given the side lengths and right triangles shown here? Again, I'll give you 2 minutes to think about that, okay? And we'll have a look at the solution together. I'll give a hint. Usually you can break the complicated areas into more manageable pieces. For example, triangles and quadrilaterals. Okay, of course, if you have finished, please give me your answer in the chat box, okay? Alright, if you have finished, let's have a look at the solution here. So basically, we can connect BE, right? If you connect BE, you break the shape into two parts. One of them is a right triangle, which is very easy to find this area, right? So first of all, we know the area of right triangle ABE can be calculated by using 1/2 of one side, another side, and this gives us 3 squared 2 over 2, right? And okay, seems like BEDC is a square. Well, let's verify if this is true. Well, first we can find the length of BE, right? The length of BE can be given by 3 plus 6 here, which is 3, right? So as you can see here, CD equals D equals BE equals BC. So basically, BEDC is a rhombus. And the interior angles, one of the interior angles is 90 degrees. So basically, BEDC is actually also a square, right? And we know the area of a square is also easy to find. So the area of BCD is 3 squared, which is 9, right? And therefore we know the area of ABCDE is the sum of these two numbers, which is 9 plus 3 squared root 2 over 2, right? Any questions? Okay, if no questions, let's consider another question here. Can you find the area of a regular hexagon with side length 8? Well, a regular hexagon has 6 sides, right? And because it's regular, so each side is equal or congruent. Something like this. Alright, have you finished? Again, we could start by breaking the hexagon into pieces we could handle, right? Since the angles of a regular hexagon are each 120 degrees, so the long diagonals like this can split each angle into two 60 degrees, right? So this angle here is also 60 degrees. Therefore, each of the little 6 triangles formed by drawing all 3 long diagonals is equilateral. So for a equilateral, if you know the side, of course you know the area of that equilateral triangle, right? The area of such a triangle is 8 square root 3 over 4, right? Which is 16 square root 3. Therefore, the area of the regular hexagon is 16 square root 3 times 6, which is 96 square root 3, right? You get it? And this example tells that many problems involving regular hexagons can be tackled by dissecting the hexagons into equilateral triangles. Any questions? Alright, then let's see another one. Okay, can you find the area of regular octagon ABCDEFGH with side lengths 4? Any ideas? Okay, let's have a look at the solution together. So a regular octagon has 8 sides, right? 8 equal sides. Basically shape like this. And also note that the interior angle of a regular octagon is 135 degrees, right? Did you get it? And of course, this angle is also 135 degrees. So if you extend the two sides, well, let's call this point A, B, C, D, E, F, G, H. So if you extend A, B, and DC, they'll meet somewhere here. Let's call this point X. So we know this angle is 45 degrees. This angle is 45 degrees, and this is a right angle, right? And similarly, extend these sides. And each of the angles here is a right angle, and therefore we have a square X, Y, Z, W, right? Because this side equals this side, AB equals CD, and all of the sides here are equal, and all of these sides of the octagon are equal. Then xw equals wz equals zy equals yx, right? Therefore, x, y, z, w is actually a square. And then we know the area of wxyz is actually wz squared, right? Can you find wz? Of course, we can find that. That equals wh plus hg plus gz, right? Squared. And we know that hg is 4. Then this side is also, ah is also 4. Then we know that wh is actually 2 square root 2, right? So gz is also 2 square root 2. So that equals 4 plus 4 square root 2 squared. And that gives us 48 plus 32 square root 2. And then we know the area of A, B, C, D, E, F, G, H should equal the square W, X, Y, Z subtracted by the area of 4WAH, which is 48 plus 32 square root 2 minus WAH is 4 times 1/2 of 2 squared 2 squared, right? And this gives us 48 plus 32 square root 2 minus 16, and this gives us 32 plus 32 square root 2. Did you get it? This is our final solution. Okay, have a look at the solution here and let me know if you have any questions, okay? And if you don't have any questions, now let's turn to a more general problem of finding the areas of regular polygons. So let's consider this example here. The center of a regular polygon is the point inside the regular polygon that is equidistant from all of the vertices of a polygon. Let the distance from the center of a regular n-gon to one of its sides to be k, and the length of each side of the n-gon be s. Can you find a formula for the area of the n-gon in terms of kn and s? Okay, let me draw you a diagram to illustrate the situation here. So suppose this is your n-gon. And you know the length of OP, which is k, and length of each side is s. So AZ is s. Can you find the area of the n-gon in terms of kn and s? And actually OP has a name. The distance from the center to the side of the regular polygon is sometimes given the name apotheum. From the center to its side, distance is called the apotheum. Okay, I'll give you 3 minutes to think about this question by yourself, and then we'll have a look at the solution together, okay? Alright, have you finished? Okay, so we can cut the regular polygon into n triangles here by connecting the center to every vertex, right? So one such a triangle is OAZ, which is shown here. The altitude to side AZ of this triangle is distance from O to the side of polygon. And we know this distance is K here, right? So we have the area of triangle AZO is 1/2 of the length of AZ and length of OP, right? Which is 1/2 of KS. And the polygon consists of n such triangles, right? So the area of the n-gon is 1/2 of k times s times n, which can be simplified to nks over 2. Did you get it? And actually you could use this as a theorem to find the area of n-gon. So let's make a summary here. So the area of a regular polygon is half its perimeter times the distance from the center of the polygon to a side, because n times s is actually its perimeter, right? Okay, have you finished? Okay, then let's put what we have learned so far together to solve some typical polygon problems. So let's have a look at another problem here. Suppose we have a pentagon ABCDE here. Diagonals BD and CE meet at point Q. Can you find the angle of BQE? Another typical angle chasing problem, right? Okay, first of all, if it's a pentagon, we know the interior angle is 108 degrees, right? And EDC is isosceles because this side equals this side. And then you could immediately find angle EDC and angle DCE, right? So angle DCE equals angle DEC, which is 180 degrees minus 108 degrees over 2, which is 36 degrees, right? And similarly, we have angle CDB is also 36 degrees, right? And therefore, angle CQD equals 180 degrees minus angle QDC minus angle QCD, right? You see that? Which is 108 degrees. Therefore, we have angle BQE equals angle CQD, which is 108 degrees because they are vertical angles, right? Any questions? Okay, no questions. Let's have a look at another one. Can you devise a formula for the number of diagonals in a polygon with n sides? For example, if you have a polygon here, it has n sides. How many diagonals can you devise inside the polygon with n sides? Well, if n equals 3, we don't have any diagonals, right? If n equals 4, we have 1, 2, right? If n equals 5, we could have 1, 2, 3, 4, 5, right? So how about in general, when you have n sides, how many diagonals can you devise inside the polygon? Well, let's have a look at the solution together. First we could consider a single vertex A, right? A is connected to two other vertices by side. That leaves us n minus 3 vertices to which A can be connected by diagonals, right? So from one point A we have n minus 3 diagonals. Since there are n vertices and each can be connected to n minus 3 others by diagonals, there appear to be n times n minus 3 diagonals, right? However, this counts each diagonal twice. Did you notice that? Therefore, you have to use this number divided by 2, right? Why it's used twice? Because once for each endpoint, right? So the total number of diagonals in the polygon with n sides is given by this formula. So you could also use this as a theorem, okay? All right, then let's see another question. A, B, C, D, E, F, G, H is a regular octagon. Can you find the ratio of AE over BH? Any ideas? Okay, so note that BH is one of the diagonals, right? Is it congruent to AC? Length of BH should be equal to AC, right? This is very easy to prove. And how about CE? CE also has equal length with BH, right? And how about EG and AG? We could prove each of the lengths here is equal to the length of BH, right? Can you see that? Then actually ACEG is a square, right? Can you see that? Because you can find this angle here, you could find this angle, then this angle is 90 degrees, right? Okay, so basically you have a square and AE is actually the diagonal of that square, right? Did you notice that? So basically you are trying to find the ratio between a diagonal of a square to one of its sides, right? We know that ratio is square root 2, right? Because this angle is 45 degrees. If this side is x, then this side is also x, right? Then that side is square root 2x. So AE over BH is just square root 2x over x, which is square root 2, right? Any questions? Okay, then let's consider another one. In the star diagram as shown on the right, can you find the sum of these angles, A, C, E, G, and I? We could not assume the pentagon in the middle of the star is regular. It's not necessarily regular, but we could still find the sum of these the 5 angles. How we could do that? Okay, any ideas? Okay, so what we know here is sum of the interior angles of a pentagon, right? And if we can establish a connection between these 5 angles and the interior angles here, then probably we can solve this problem, right? So let's label these 5 angles here as A, B, C, D, E. Then first of all, we know in triangle, let's use some letters here, B, D, F, H, J. Well, if you could consider this triangle here, A, E, H, if you consider this triangle, then we have angle A plus angle plus E plus angle uppercase E is 180 degrees, right? Actually, we have 5 such triangles that we can use. And if you consider another triangle, then angle C plus A plus angle G is also 180 degrees, right? Similarly, we have angle E plus angle B plus angle I is also 180 degrees. And angle G plus C plus angle A equals 180 degrees. And angle I plus D plus angle C is also 180 degrees. So if we could sum up all the 5 equations, then we could see that there is a sum of 5 angles, right? This will give us angle A, well, twice of angle A plus angle B, twice of angle A plus angle C plus angle E plus angle G plus angle I, and plus A, B, C, D, E, right? And this equals 180 degrees times 5 gives us 900 degrees, right? Again, because we know A plus B plus C plus D plus E is sum of all the interior angles in the pentagon, which is 5 minus 2 times 180 degrees. Sorry, which is 540 degrees, right? Therefore, we know angle A plus angle C plus angle E plus angle G plus angle I, which is a desired sum, right? Equals 900 degrees minus 540 degrees over 2. And this gives us 180 degrees, right? Did you get it? So as long as you have a star, the sum of these 5 angles equals 180 degrees. Any questions? Okay, if not, let's have a look at one last example. ABCDFGH is a regular octagon with side length 12. Can you find the area of ABDG? Again, we have a regular octagon. And we know the side length is 12. What is the area of ABDG? Any ideas? Oh, actually, ABDG is a trapezoid. I'm not gonna write the proof here. You can try to prove this by yourself after the class. Okay, you can start from there. We could dissect the octagon into pieces we can handle, and we know altitudes of the trapezoid can often be useful, so we could draw diagonals AF and BE. These are each perpendicular to GD and FE. Again, I'm not gonna write the proof here. Try to prove this by yourself. It's not that difficult after the class, okay? You can prove AF is actually perpendicular to GD and B is actually perpendicular to GD as well. Since GD is parallel to FE, then we have angle FGD equals 180 degrees minus angle GFE, which is 45 degrees. So triangle GXF is actually 45, 45, 90 triangle, right? Therefore, we know GX equals GF over square root 2, which gives us 6 square root 2, right? Similarly, YD equals 6 square root 2. XYEF. So let's call this point X and Y here. Sorry, I forgot to label them. XYEF is a rectangle. So XY equals EF equals 12. Therefore, base GD of our trapezoid has length 12 plus 12 square root 2. This is the key to this problem. Before we go through tricky computations to get AX, we can note that by symmetry we have AF is actually equal to GD, right? Alternatively, you can also use HL congruence to show triangle AXG is congruent to triangle DXF. Therefore, we have AX equals AF minus XF, which is DG minus GX, which is 12 plus 6 square root 2. Therefore, we can calculate the area of ABDG, which is 1/2 of AB plus DG times AX. And this is 1/2 of 24 plus 12 square root 2 times 12 plus 12 square root 2, and eventually you will get a number like this: 216 plus 144 square root 2. Alright, so have a look at the solution here. And if you don't have any question, please find the homework and today's notes together with a video recording. And I'll see you next time then.